So today we'll learn how to find convective heat transfer coefficient or heat flux of any irregular body if we are having the characteristic length of the duct as well as the irregular body which is given to us. For example, here I'll show you. There's a solid body. This one. I'll show you. This one is the solid body, and this is the rectangular duct which I've named as cover box. So this will be modeled inside SolidWorks. So what is happening over here is there's an inlet which is named as lid 1. I've put a lid onto the exposed surface, lateral surface, and the lid 2 at this one. This is the outlet. There's a solid body which is in my case is cuboidal in space in shape, and there's a duct which is also cuboidal in shape, but it is placed, it is there in which solid body is present. So what is happening is one surface of this I'm putting some heat onto this surface or some temperature onto this surface, and then I am allowing it to be here. So there is some flow which is coming from this side, which I'll choose as air, and it is going from this side. So I'll try to show how it is the heat flux of any surface, because it won't be just this surface which heat flux I will be calculating. To calculate heat transfer coefficient is a really tedious task if you are trying to do in practical purposes, but in CFD you can find it very easily with the help of computation, flow simulations, and the other parts. If you're allowed to give boundary conditions and what will be the inlet flow, and I'll show you how with the change in the values of inlet flow the heat flux also changes, because what CFD does is it takes into account all the equations, the moment equations, the continuity equations, and then it also applies the Fourier's laws and all, and what it does, it accounts for all the temperature which changes inside the whole system. So temperature at every point is known during the CFD, and with that change in temperatures, it is allowing itself to find the heat flux coefficient, the convective heat transfer coefficient of any surface. We can have many results, and if you specifically want heat transfer coefficient of any body, we can choose that. But now I'll show you how I model this. So yeah, this is an easy model which I've just taken as cuboidal shape, but you can take any part, and that same CFD can be applied to anything. If suppose you're having a polygon of 8 surfaces and you want one surface, you want to know what is the heat transfer coefficient at one surface, that also you can do. So what I have done here is I've taken a duct and there is a solid body inside it. So what I'll show you just how I model the solid body. First I'll show you the solid body, and then I'll show you how I made the duct. So I'll open it. So there's a solid body. How I made it is just easy. I'll show you. There's a sketch which I first designed because I had the characteristic length, so I made a rectangle. If you have a normal solid body, SolidWorks knowledge, then you would know how to build the solid body. So I'm taking this rectangle of some length and breadth, and what I did is I went into feature and I chose extruded base, and I extruded it to some length. But keep in mind, I didn't do this as thin feature because I want some material inside it. I don't want it to be hollow, so I didn't choose the thin feature and I didn't choose the cap ends. So into the feature I went for extruded boss and base, and I extended it to 0.007 meter, which is 7 millimeters, which was the height of the solid body. And then I just checked it, and there you go, I had my solid body. So this was how solid body was modeled, which is very easy one. Again, for the rectangular duct, what I did was I first modeled a sketch. My first place was this, my first, yeah. So first I modeled this with the help of the length that was given to me. I chose the rectangle here as well, and then I boss extruded it, as you can see, to some width, which was the height of the duct. And then what I did is was, I'll show you just, I put the thin feature. You can see the duct is hollow, which is has to be, because I have to place a solid body inside it. So this is hollow, but what I'll show you is there is some cut extrude here, which should not be here, because I just told you I had put cap ends on here. When you are boss extruding, there is a thin feature, and along with the thin feature there comes a cap ends. I had to do a cut extrude, if you can see there, which how I did. If you want to make a hole inside a hollow body or a solid body, what you have to do is you first select the surface, you go into sketch, you sketch something over there with the help of obviously a rectangular or something. For example, see, there I did something, so you can actually do that. Okay, you can actually do those things. So this way I went into this surface, and this was, the surface was closed, it was not open, but I needed it to be open. So I'll tell you what I did was, I went onto the surface because this whole surface was closed, and I went on to sketch, and I modeled a sketch onto the surface. So if you see, this is the rectangle that I made on this surface, and then I went to features, which in this case will be showing extruded surface because this is already done, but for this sketch. But when you sketch it, you will see there is a extruded cut over here, which will allow you to take the length from here to the complete here, and then you will have extruded cut. So this is how duct was made. Fine. So I'll go back instantly to the so this is my model, and what now I needed to do, because if I have to do this CFD, I have to close it. There should not be any open surface. So I put a lid onto the first surface. For that, what you do, you just go onto the tools and flow simulations, and you select tools and you create lids. By lids, you will automatically select the surface, and it will create a lid over there. The main part is the CFD part, I mean the flow simulation part. So you go on to the flow simulation, here it is, and I'll show you the general settings that I have done. You first go to tools, and then you go to flow simulation, and in project you select wizard. What you have to do in wizard is what I'll show you just now, but I'm not creating a new wizard, keep in mind that. So I'll just show you what have I done, what are the general settings that needed to be done in the wizard from there. So first you have to choose external. Internal should not work in this case, and like there will be changes in study and there will be changes in the value, so external is preferred. Heat conduction is solid is must if you are really doing convective heat transfer coefficients and more. There will be in the solid body there would be heat conduction, so we should take into the account heat conduction, and no other was selected. So this was the analysis. For fluids, as I said, air will be passing through, and we will be checking if there is any change in heat transfer coefficient based on the values of the flow that we are passing. So in the gases, we are just selecting air, which is obviously because air we have selected, so air we have here, and it was the flow type was laminar and turbulent, because it depends upon the values of Reynolds number and all. and the flow, actually the value of the flow and inlet flow rate which is coming from there. So this was about solid fluids, and I'll check into solids. For solids, I have taken the body as carbons, cast carbon steel, but you can take any type if you want. It depends upon the whatever value you are having, and there are plenty of materials provided over there. For ambient and initial conditions, I have taken the pressure, thermodynamic pressure as the atmospheric pressure and 20 degrees Celsius. So this is what you have to do in general settings. I'm not doing it again, I'm just showing you what I did, so there will be some time efficiency. In the computational domain, of obviously after we have done this, there will be assembly. Okay, one part which I'll be not showing you is how to do an assembly. I hope you know that, but in case you don't, you have to choose these mate surfaces. Okay, so what I have done is I have chosen, like, first you have to go into, I'll just wrap it up in a minute or so. First you have to go into new, okay, and you have to select assembly from that. In the assembly you will have options like, you go to insert and there is a component and you choose existing part or assembly. So you select from there the bodies which you want to assemble here, because they are initially in the part. You see, these are the parts, the 4 parts of the body, and we have assembled it. So how do I put, like, I want to place this solid body inside the duct. So how do I do it? I do it by doing the mate feature. You see the mate feature over there. So you go into assembly, you choose mate, and there is some distance between solid body first and solid body and cover box, right? So I'll show you edit feature. So as you can see, I have chosen the 2 faces, the cover box of first and solid body is this surface. So if you see closely, I'll try to show it to you. It would be better this way. So between these 2 surfaces there is gap. How much it is? It is 0.001 meter. So this its top surface, and this it's the top surface of the solid body, both have a gap of 0.001 meter, which is given over here. And then we are selecting the mate. This is what I have done first for this one, but that does not tell me where should I put this one with respect to the other ones. So I have to choose another mate, which is this one, solid body, and this is telling me that this should be, and the gap between the lateral surface of this one and the lateral surface of duct should have a distance between them, which is also, I think, somewhere around 0.004 is the distance, because it is larger in space. So this is what I have chosen, and so I have placed it there. This is how you do mates, and you place bodies where you want to in the assembly feature. So going back to the flow simulation part, so then we select the fluid subdomain. For fluid subdomain you don't have to do really anything. You just have to go first select the sectional view and then put where you want your fluid to pass through. If there is any leakage, the fluid subdomain will tell you, and that's one advantage of using it. For solid body, as I said, I put carbon steel, which you can do. Now main important things are here are boundary conditions and the heat sources that I have put over there. If you see inlet mass flow, I have given this as inlet and this as inlet and this one as outlet. Inlet mass flow is 0.0021, which is the value that I have taken here. Okay, so what you do is you just do it sectional view first, because from here you will be getting the top surface of this body, not the inside surface. So you first have to do sectional view, which I'll first do it for you. Okay, so how, yeah, right now you can select this, but when it was not a sectional view, we were not able to select it, we were getting the top surfaces. So inlet mass flow I have select here. So you go into boundary conditions. Wait, you go into boundary condition, you go right click, insert boundary conditions, and you will get plenty of boundary conditions like inlet mass flow, inlet mass flux, whichever value you have for inlet, you can put it there. Here you will put the value of the mass flow, and then thermodynamic parameters. If the air is having some temperature, it is hot air or cold air, based on those you can put the values here, and then you apply the surface, which surface you wanted, because here you will have to be selecting which surface is your inlet mass flow, the values of the inlet mass flow and their thermodynamic parameters, and there you go, you have your boundary conditions. Similarly, I've done here inlet mass flow. I put all the inside surfaces real walls. For real walls you don't have to do much anything, right? You just have to go on walls, select a real wall, and just select the whole surfaces. Like this one I want as real wall, this one. So all the other parts of the rectangular, inside part of the rectangular duct and the outer side part, I've selected as real duct, and there you go, all the parts are done as the real walls. So that is done here. I'll be deleting this because that is already done. And then there is the outlet part. So outlet part I'll be doing, as you see, I've put it as environmental pressure, which is like it is open to the atmosphere. That is what the conditions is saying. So these are the boundary conditions, and now as I said, I want to put the bottom surface of the solid body as a heat generation part. So you see, I've chosen heat surface heat generation rate from flow. If you go to flow simulation and you go to tools, you will see, wait, no, not this. Yeah, from insert I'll be having surface source. So I'll choose surface source, which is the heat generation, and I'll put this, because to select this one I also have to get this sectional view. So for sectional view I'll be doing from this side to this one, and there I selected the bottom surface of the body as 20. It is generating 20 watt. So that's the heat that is going from that surface. So I've taken this. Okay, this is not the bottom surface, this is the side surface that I've chosen, but you can select any type. So one part of the body, it is generating 20 watt, and there you go. So this is how I go for the heat sources. And for goals, I have selected my goals as heat flux convective 1, which I want, average surface heat flux, and average surface heat flux for convecting. This is the global goals, and this is the surface goal. This is what GG and SG means. So there I created the mesh, global mesh. I put it as fines, and somewhere around 6. So, and then I'll have to do nothing but just go onto the project and run it. New simulation and mesh, and it will take some time, and then it will give you the values if you go into the plots. So see, example for here, I had the solver was finished for the first part, and if you see, it took 146 generations iteration, sorry, and it took somewhere around 43 minutes because my laptop is slow and this whole assembly is too big for it. So it takes some time, and after that you have to just come here and put a surface plot, for example like this, and it will tell you what is the temperature of these surfaces. You just have to go here and select the surfaces, and it will tell you what is the surface plot up there, and in the goal plot it will tell you what is the surface goal or heat flux coefficients, and then you will be having your values. So this is how you do an analysis of conjugate heat transfer coefficient, where if you have any body and you want a convective heat transfer coefficient of the body, solid body, which is of any irregular shape, and it is